Good morning, everyone. Today we're doing Unit 5 review. So if you'd like to take a minute and pause the video to fill out some of the vocab of the terms that we learned in this unit, go ahead and do that. Okay, once you've paused the video and written down all the vocabulary, I'm just going to discuss what each of these things are, and we've talked about them lots in this unit. So first of all, this whole unit is about a very particular type of periodic function, but a periodic function is a function which repeats horizontally. In particular, in this case, we're looking at sinusoidal functions, which are just periodic functions with a wave. So I would just say, well, we are looking at sinusoidal ones, and these are periodic wave functions. So they repeat that wave pattern for sine and cosine functions. So the general equation for these sinusoidal functions, we've looked at both sine and cosine. They're written there for you, and we talked about what each of these variables represent. Okay, it's important that we understand what a, k, d, and c represent in terms of our cosine and our sine function, which they represent the same for both. So we'll explore those now below. So one of the characteristics of these sinusoidal functions is the period, which is the length of one cycle. For our base function, it's 360 degrees, but it's different for all functions. So we can determine our horizontal compression or stretch from that k value in our function. That k value will also help us figure out our period. So when a function is being horizontally compressed by a factor of k, then we divide all the y values. So we divide the y values by k. And with that k, we can also find out our period. So to find k, we can take 360 and divide it by the period if we know the period. If we know the k value, but we need to figure out what is the period, then we would take 360 divided by k to figure out what is the period. The next transformation is a horizontal shift. So that is how much we're moving left to right. And the important part here is to remember that if it's a plus d, it shifts left. And if it's a minus d, it shifts right. So within the equation, if it's plus or minus. The next transformation is our vertical stretch, which also is our amplitude. So our amplitude is represented by that variable a, and it's the vertical distance from the axis to the maximum or minimum. And we can figure out what the amplitude is when we know the maximum minimum. So if we're given a graph, we can identify our maximum and our minimum, and then use that information to find our amplitude. This a value also represents our vertical stretch or compression. And so with that value, we can multiply our x values by a to find out what they will be over the transformed function. The next transformation we looked at was our vertical shift, which also represents the equation of our axis. So remember, the equation of our axis is that horizontal line halfway between our maximum and our minimum. And we can determine that, again, using our maximum and minimum, adding them together and dividing by 2. That c value that is our equation of our axis is also our vertical shift. And what's important to remember there is that if we have a plus c, it's going to shift the function up. And if we have a minus c, it's going to shift the function down. So we're just going to look at a few of the things we covered in this unit on the review. So first off, graphing these sinusoidal functions. We learned 2 methods for doing so. We learned to either list our transformations to graph them, or use a mapping tool, creating a table of values to transform the key points on that base function. So this first one, we are going to graph by listing our transformation. So we're going to use that method first, and then we'll take a look at the other method. So we have a sine function here. So let's first graph our base sine function. We know that where the key points are. They're at 0, 90, 180, 270, and 360. Right? And we know that they go from the axis to the maximum, back to the axis, then to the minimum, and finally back to our axis. All right, so if we're going to list our transformations, let's identify our variables here. So we have our a, our k, our d, and our c. So our a value represents a vertical stretch. Maybe I'll just put a vertical stretch by 3. So that means we're going to take all of our y values and we're going to multiply them by 3. That's what our vertical stretch is, right? And then that k value represents our horizontal compression. In this case, that's by 3 again. So that means we're going to take all of our x values and we're going to compress them or divide them by 3. The next transformation we have there on our d variable is going to be a phase shift. And in this case, our d variable is 45 degrees. And since it's a minus, it's going to be 45 degrees to the right. And that last variable, our c, is a vertical shift. And because it's a plus, that means we're going to go up 1. Okay, so we're going to take all these transformations into account to transform this graph, and we're going to do them actually in the order that we list them. So we're going to do the vertical stretch, then the horizontal compression, then our phase shift, then our vertical shift. So let's try to transform this. So my first point is here at 0, 0. So I have to vertically stretch that. Well, if it's at 0, then if I stretch it by 3, it's still going to be 0. My horizontal compression, I'm taking my x and I'm compressing or dividing it by 3. So that stays at 0. Then I'm going to do my phase shift, which shifts this point 45 degrees to the right, so somewhere here. And then I'm going to do my vertical shift up 1. So that point is now going to go here. Okay, so now we'll look at our next point. Our next point is at 90 and 1. So my y value is at 1. So I'm going to start by vertically stretching that by 3. So that's going to bring the point up to 3 on my y-axis. And then I'm going to compress that 90 by 3. I'm going to divide 90 by 3, which brings me to 30. Okay, so let's see, we stretch it up, and then we compress it back to 30. And then we're going to shift it right. So we're at 30 right now. We got to go back 45. So that's going to put me at 75. So here's 60, and here's 75, somewhere between our 60 and our 90. And then finally we have to shift it up 1. So we're going to be right there. Okay, if we take our next point, we're going to do the same thing. So we're at 180 and 0. We're going to vertically stretch that. Well, if we're at 0 and we stretch it by 3, it doesn't do anything. But my 180, I'm going to have to compress by 3. So that's going to bring me down to 60. And then I have to move that 60 45 degrees to the right. So that's going to put me at 105, which is somewhere between my 90 and my 120. And then move up 1. Okay, I'm going to go ahead and pause the video and get you guys to transform the next 2 points. Okay, so there are the key points transformed into the new function. We're going to identify our amplitude, our axis, and our period, and then maybe we can see if we can extend this graph for another cycle. So our amplitude is just the a value in my function, so our amplitude is 3. Our axis, remember, is going to be the c value in our function, so that happens at 1. And then our period, well, normally our period is 360, but we're going to divide that by our k value, which is 3, to figure out how long is each period. So it says a period is going to be 120 degrees. So if we know that, we can figure out how often our... So our key points are every... And remember, we're going to do 120 divided by 4, which is going to equal 30 degrees. So when we're plotting our key points on here, we should have a key point every 30 degrees. So knowing that, we could extend this function, right? We can identify that this is our axis here at 1. And we know that we're at our axis now, so 30 degrees later, we're going to have to go up to our maximum. So right now, I'm at 165. 30 degrees later is going to be 195. So at 195, we're going up to our maximum, which is 4. It'll be up here. And then 30 degrees from 195 is going to be 225. And we're going to come back down to our axis. And then 30 degrees later, we'll be at 255, and we'll be at our minimum. And then finally, 30 degrees later, we'll be at 285, and we'll go up to our axis again. So we'll just connect those lines. Okay, and there's that function extended 2 times. Okay, so this next example, we're gonna again sketch the transform function, but this time we're gonna use that mapping tool. Use the mapping tool. So, and then we will again identify our amplitude, our equation of our axis, and our period. So we have a cosine function. Let's start by writing our key points for our cosine function. So we have our theta, and we have that y equals the cos of theta. So our key points, we've done them lots now, 0, 90, 180, 270, and 360. And remember, our cosine starts at our maximum, goes down to our axis, then down to our minimum, back to our axis, and then back to our maximum. So we need to look at our transformation that's happening here. And remember also that we need to factor out anything that's in front of that theta. So let's factor this out. So when we factor it out, we should have 1/2 cos. And I'm factoring out that 2, so I'm going to create a second set of brackets. We'll have theta, and we take a 2 out of 180. It's going to be 90 now, minus 3. Okay, so we have all these things happening. We have to remember what do they represent in terms of our transformation. So anything inside our brackets is going to affect my theta, and anything outside our brackets affects our y value. So we have theta is going to be divided by 2, because that's our k value. And then we're going to add to it that 90, which represents that horizontal shift to the right 90 degrees. And then on our y values, we are going to multiply by our a value, which is 1/2, so 1/2 times our y value. And we're going to subtract 3, which represents that vertical shift down. Okay, so for all my thetas, I'm going to start this, and I'm going to get you guys to finish it. I'm going to divide by 2 and then add 90. So this first theta is 0. So 0 divided by 2 is 0. 0 plus 90 is 90. Okay, the next theta, 90. 90 divided by 2 is 45. 45 plus 90 is 135. Okay, I'm going to do a couple y values, and then I'll pause and get you guys to finish. So now I'm going to take all my y values, multiply them by 1/2, and subtract 3. So my first y value is 1. So 1/2 times 1 is 1/2, and then minus 3, you're going to have a negative 2.5. 0 times 1/2 is 0. 0 minus 3 is negative 3. Go ahead and pause the video and finish that table of values for your thetas and for your y's, and then see if you can plot both the base function of cosine as well as the transformed function of cosine. Okay, so there is the function transformed. You can see that it's been condensed quite a bit, and that it's also been shifted down. So let's identify some of those features they asked us to, and then see if we can maybe extend the graph a bit. So our amplitude, remember, is just our a value, which in this case is 1/2. Our axis is just our c value, so that's going to be at negative 3, and we can even plot that axis at y equals negative 3. That's our axis. And then our period is going to be found by taking 360 and dividing it by our k value, which in this case is 2. So our period equals 180 degrees. And you can even see that to go from here to here, right, that's going from 90 to 270, that is 180 degrees. Okay, so you can see that that is, in fact, our period. We can also use that period to, again, find how often are our key points, so that we could extend that graph. So key points are every, and remember, we're going to take that period and divide by 4 to see how often our key points are. So 180 divided by 4 is 45 degrees. So every 45 degrees, you're going to have another key point. So if we wanted to extend this graph, we could do that. So if I was at 90 and I wanted to extend it, well, I'd have to go over 45 degrees, and then I need to come back down to my axis. So that'd be 45 degrees and then back to my axis. And then if I wanted to go another 45 degrees right to my y-axis, I'd go down to our minimum there. And same going the other way. So if I'm at 270 and I extended it 45 degrees, I'd go back down to my axis. So you see we can extend that graph once we know how often those key points are. Okay, great. And then let's just label that so that we know that this one is f of x equals 1/2 cos, and then 2 theta minus 90 minus 3. And this one up here was our base function for cosine. Okay, great. So now let's look at writing some equations. I'll try one and then I'd like you guys to give it a try. So when you're given some information, you should be able to determine the equation based on the transformations that are provided to you, or based on the characteristics of the graph, which we should now be able to translate into those variables that are represented in the function. So let's try the first one. So write the equation of the sine function. So we're going to use our sine function here with an amplitude of a period of 90 degrees, shifted right 40 degrees, and then shifted up 3. So an amplitude of a means that our a variable is going to be 5. Our period is 90 degrees, so we need to figure out what's our k. So remember, to find k, we're going to take 360 and divide it by a period, which is, in this case, is 90 degrees. So we're going to do 360 divided by 90, so k equals 4. If it's shifted right 40 degrees, that is our d variable, which means it's going to be a minus 40. And then finally, shifted up is represented by that vertical shift, or our c variable, so that's going to be a plus 3. Let's just remember one more time what that function looks like. So it's going to be y is equal to a times the sine of k, and then in brackets theta minus d plus c. So all that information we've just been provided, we should be able to write our sine function. So y equals, our a value is 5 times sine, in bracket our k value is 4, another bracket, theta minus our d value, which is 40, plus our c value of 3. Okay, in the next example, they give you those variables, but they give it to you in terms of the transformation or the characteristic on the graph. So see if you can figure out what the sine function would be for that next one. Pause the video, try that now. Okay, there's that function transformed, making sure you can identify what's your a, k, d, and c, and then plug it into the equation. Okay, now we're going to look at determining the equation from the graph, not just being given information, but if you have a graph, can you identify the equation? So it says to determine the equation of the graph below in terms of the cosine function. So remember that our cosine function starts at our max, as does this graph. So since this graph starts at the maximum, we're going to require no phase shift, right? We don't have to shift it left or right at all for cosine. So what can we identify in this graph? Well, we can see where our maximum is, and we can see where our minimum is. So hopefully we can use that maximum and minimum to help identify some of the characteristics we know. So our max is at 6, and our minimum is at 1. So we've learned that we can identify our axis from that, which represents our c variable. So our axis is going to equal our maximum plus our minimum divided by 2. So our axis is going to be at 3.5. So if I wanted to draw that on there, we could draw our axis there, and that might help us identify some other characteristics. So our axis is at y equals 3.5. Okay, the other thing we can identify with our maximum and our minimum is our amplitude, which is our a value. So our amplitude is going to be our maximum minus our minimum divided by 2, which is going to equal 2.5. All right, what other variables do we need to represent? We need to figure out our k and our d, which is our phase shift. So let's talk about, we already identified that we don't need a phase shift for this one because the graph starts at the maximum. So we have a phase shift of 0. Now for our k value, remember our k is, we found somewhere by using our period, we know that our k value is equal to 360 divided by our period. So hopefully we can identify our period from looking at our graph here. So our graph starts at 0 here, it goes down to our minimum, back to our axis, and then up to our maximum at 720 degrees. So that tells me my period is 720 degrees. So our K value will be 360 divided by 720. So K will equal 1/2. So now we've found all of those values for our variables. We should be able to just plug those right into our cosine equation. So our cosine equation, is going to be y is equal to our a value, which is 2.5, times cosine, and then in brackets, our k value, which is 1/2, theta. We don't have a phase shift here. Our phase shift was 0. And then plus our vertical shift, or our axis, which is 3.5. Okay, if we were to determine the equation of the same graph in terms of sine, well, remember, we have to take a look at where does sine start. Okay, our sine usually starts at the axis. So we need to figure out how much was this graph shifted if we were going to truly represent this with our sine. So here's the first time we hit our axis. So that is a shift of 180 degrees. So for our sine curve, we need a phase shift of 180 degrees to the right. So remember, that is going to be represented by our d value, our d variable. So we have a phase shift. And if we're moving it to the right, it's going to have to be a minus 180. But notice here that our phase shift is at 180, but then from the axis, the graph goes down. Well, with our sine curve, we usually go from the axis and go up. So if we're going down, that means we're flipping or we're reflecting that function. So we're going to need to have a negative a value here. So our amplitude will remain the same, other than it's going to be a negative because we're reflecting that sine curve. So sine, and then my k value remains the same, 1/2. But now we have a phase shift. So we're going to have theta minus 180. And then plus that axis, or a vertical shift, of 3.5. And then the last question here is, which function, sine or cosine, should be used? Hopefully we all see that cosine should be used because no phase shift is required for the cosine. So we want to make our lives as easy as possible. And so if we don't even have to identify one of those variables, then that's obviously the easier choice. Okay, finally we're going to look at some word problems, and then we'll be done with our review. So we'll try some of this, and then I'll get you to pause and work on some of it on your own. So the movement of a piston in an automobile engine is modeled by the function d of t equals 50 times the sine of 9,000 t plus 8, where d is the distance from the crankshaft in millimeters, and t is the time in seconds. So let's just highlight so we make sure we know that d is the distance in millimeters and t is the time in seconds. So what is the period of this function? So remember that the period we can identify with our k value. So we have to see, well, where's my k value? This 9,000 is going to represent my k value. So period equals 360 divided by k. So our period is going to equal 360 divided by 9,000. Okay, and if we reduce that, okay, we should be able to reduce actually that by 360. We're going to get 1/25. And remember that that represents our time. So this is 1/25 of a second. And so that says, what does it represent in this context of the problem? Well, that tells us how long it takes for the crankshaft to do, for the piston to do one complete cycle. So it completes one cycle in 1/25 of a second. So that means the piston completes 25 cycles in 1 second. Because one cycle is completed in 1/25 of a second, so the piston completes 25 cycles in 1 second. Okay. If the driver sped up, which number in the equation would change? Would it increase or decrease? Well, think about that for a minute. If the driver sped up, if he started going faster, then wouldn't our period decrease, right? Our period it would take less time for the piston to complete one cycle if the driver decided to speed up. So the period would decrease. So in order for the period to decrease, remember the period is affected by that K value. So if the period is decreasing, that means that fraction of 360 divided by K is getting smaller. And the only way to make that fraction smaller is to make our denominator bigger. So that means the K value is going to increase. So the K value would increase because if you divide 360 by a larger number, the fraction would decrease. Right? So if you're trying to make a fraction smaller, then you need to either increase the numerator you'd either need to decrease the numerator or increase the denominator. We can't control the 360, that's what it is, but we can fluctuate that K value. So if we increase that K value, it will decrease our period overall. Okay, pause the video and see if you can determine the minimum, the maximum, and the amplitude of this function. Okay, so there's your maximum, your minimum, and your amplitude. We can identify our axis because that is just that C variable from our equation, so C is there, and our amplitude is just our A variable from our equation, right? So our amplitude is 50, and our axis, our vertical shift, is 8. So once we've identified those, we know to go to our maximum. To go from our maximum, all we have to do is do our axis plus our amplitude, and to go to our minimum, it would be our axis minus our amplitude. So that's where we get those values from. The next example, the vertical distance in meters of a rider with respect to the ground on a Ferris wheel is modeled by h of t equals 7 times the cos of 18t plus 8, where t is the number of seconds. So again here, I'm going to get you guys to pause in a minute, but let's recognize that t represents our number of seconds, and the vertical distance on a Ferris wheel, so h of t is represented by our vertical distance here. Okay, so I'd like you to pause the video and try to work through A and B on your own. Okay, there's the solution for your first two. So for the first one, we're plugging in 8 for our time, and then we're solving to figure out that the height is 2.3. So we could say, therefore, the rider's height is 2.3 meters after 8 seconds. Okay, the second one is asking you to determine what time is the rider's first at 4.5 meters. So if you plug in 4.5 for your height and then use algebra to figure out the time, you should find that time is 6.7 seconds. So therefore, the rider is first at 4.5 meters after 6.7 seconds. Okay, the last question, which there's a hint there to make a sketch. When is the third time the rider is at 4.5 meters? So if we were to draw a sketch of this, just a rough one, we could identify some of those characteristics here to help us. So we know that at 6.7 seconds, they're at 4.5 meters, but when again does that happen? So if I want to do a rough sketch of this, it says that the vertical distance in meters of a rider, right? And it gives us this cosine function. You'll notice that there's no phase shift for this cosine function. So that means that it must start at the maximum. So the rider must start at their maximum point. So if we wanted to figure out, well, what is their maximum point? That's going to be equal to our axis, which is 8, plus our amplitude, which is 7. So our max is going to equal 15. We could also figure out, well, where's our minimum then? So our minimum is going to be, again, our axis, which is 8, minus our amplitude of 7. So that's going to be at 1. All right, we could also identify, okay, well, where's my axis then? So your axis is going to be your maximum plus your minimum divided by 2. So your axis is going to be at 8. So we could just kind of plot some of this rough information. We know our maximum's at 15, our axis is at 8, and our minimum is at 1. All right, we need to know now what's happening along our y-axis though, or sorry, around our x-axis. So on our x-axis, we need to figure out, okay, well, what's the period? How often are we going to hit the period or hit those key points? So our period is going to be represented by 360 divided by our k value, which is 18. So our period is going to be 20. And then our key points are going to be and remember to find our key points, we're going to take that period and divide it by 4. So our key points are going to be every 5 seconds. So I'm going to put those along my x-axis. We need one at 5, 10, 15, and 20. All right. So we know that our graph is going to start at our maximum, and it's also going to end at our maximum, right? Because that's one complete cycle. From there, at each key point, we're going to just follow that pattern for our cosine function. So at our next key point from 0, which our next key point is at 5, we're going to go down to our axis. And then our next key point at 10, we're going to go down to our minimum. And at 15, back up to our axis. And finally, up to our maximum again. So that's why they said just make a sketch. So we know that at 4.5 seconds, or sorry, 4.5 meters, that occurs after 6.7 seconds. So if we were just going to kind of eyeball where that is, well, 4.5 meters would be somewhere in here, right? And that happens at 6.7 seconds. Well, if we look at this again and we wanted to repeat this pattern, right? This is going to repeat. So it's going to go down again. So when is the third time it's going to hit 6.7? Well, we know it's going to hit 6.7 here and at here, right? That's going to be 4.5 meters again. So if we follow that across, it's going to hit 4.5 meters somewhere over here for the third time. So that's 1, 2, 3 times. Well, how can we figure out that third time? Well, you're just going to repeat your cycle again. So if we start our cycle again over at 20 seconds, then we're going to need to go another 6.7, right? Because after 6.7 seconds in a cycle, you're going to hit that 4.5 meters again. So 26.7 seconds. So that'll be the third time we hit 4.5 meters. That's it for your review for today.